Okay. All right, so we started yesterday looking at our linear population models. And we did number 1 and number 3 so far, right? I did go ahead and post homework 7 on substitutions. That's going to be due on Friday, because we finished that yesterday or the day before that. And then Friday's quiz is going to be on substitution. So we'll check in Friday morning if there's any questions on that homework. And then the quiz will be one problem that is either a linear substitution or a Bernoulli substitution. Okay. So that's what we got going on there. Also, we've got an exam coming up a week from Friday. So practice exam will come out Friday. I'm going to grade homework today and have it back for you on Friday. Have all that ready to go. If you are pulling things electronically, the module is updated. So linear ones are the ones we did yesterday. We're going to finish those 2 and then maybe move on to non-linear ones. And then tanks will come after that. So we're working. No, a week from Friday. Next Friday, not this Friday. This Friday, quiz on substitutions. Next Friday, exam 2. Every 3 weeks is what we're scheduled for at the moment-ish. Okay. Now, right. So 1 homework, 1 quiz for Friday, exam coming up next week. So, all right, what I want to do is I want to give you guys a few minutes to work on number 2. All right. Since I did number 1 and I got you a little bit started here, we're talking about half-life. You're going to let A be your amount of carbon or some variable to the amount of carbon-14 in an object. And then when we talk about half-life, we know that the rate of change of the amount that's there is proportional to how much is there. So we have the dAdt equals K times N. In this case, I don't think they give you, I didn't read you specifically, but they don't give you an A0. But what they do tell you is that the half-life of carbon-14 is 5,600. So leave your initial amount as A0. Right? So A of 0 is equal to A0. And then use this fact that A at the amount at 5,600 years is half of whatever that initial amount is. And that'll help you find your K. So you can go ahead and start up. And I want you to solve it all the way from here. So start with the dAdt equals K times A, separate and solve, then go ahead and plug things in, because that's what I'm going to want you to show me when we do this on the quiz or the exam. Take a couple minutes. Do I have? All right, so here's the first part that I'm looking for. I'm looking for you to be able to state the differential equation. So dA dt equals k times a. To go ahead and separate it, so move the a to the left and the dt to the right. Go ahead and integrate, get your natural log of a, and take the e of both sides. And that leaves you with a equals c e to the kt. Usually I use a when I move it to the front, but I'm already using a, so I just kept capital C. And then we're using the initial condition that we don't have an initial value, so we're just going to call it a naught. When you solve for that, that's going to put a naught as the constant in front of your e. All right, so you want to be able to get to this place. Okay, now, yes, have we shown that every time we solve something that looks like this, we get something that looks like this? Yes. And on homework, that's fine. But on exams and quizzes, I want you to show me that you know how to get there. Right, so you want to start from an initial value problem and get to the model. Okay, from here, you're going to go ahead and use those constants. So we still have the a of 5600 equals 1/2 a naught to use to find the k. Okay, but I just want to check in and make sure you're all at the same place. Right, you're plugging in that condition. That a naught will cancel on both sides. So you've got 1/2 is e to the 5600k. And then find your k. So take your natural log of both sides, divide by the 5600. So that's going to give you the natural log of 1/2. And then k is the natural log of 1/2 over 5600. So the model that we're working from then is that a is equal to a naught e to the t times that ln 1/2 over 5600. So that's how we use the half-life to set up our problems. From here, we've got to go back and read and see what they want. So if I'm going back to the top, let's see. They're saying after 660 years, what percentage of the original amount remains in the cloth? Okay, so that means they want me to find what is A, right, when T is equal to 660. So we're going to plug that in. So we get A equals A naught E to the 660 over 5600 times the natural log of 1/2. Yeah, sort out what that is.
So we're assuming that the 660 was taken as of 1980.
Yes,
Okay.
that's the way it's written. This is going to be super annoying on my calculator. Let me go to Wolfram Alpha. That'll be easier. Oh, I want you to give me. There we go. 0.9215. Or 1/6 really. And when the amount is given that way, it's given as a fraction of the initial amount, then this, when you convert to a percentage, is the percent, right? So multiply by 100, it tells you that 92.2% of the carbon still remains. So that's how we do that.
If you misunderstand the word problem, at 0.6.
I mean, it depends how
So
far you get.
I'll give my example. On this, when it
Yeah.
said it was 660 years old, I thought that meant as of today it's 660. So the way I found my time is like I found when it was 0 years old, and then the time from that to 1988. So
Okay.
I got like 628, and that was the number I used.
I see. So you backed it up by X number of years. So just be careful with your reading, because from right here, it says in 1988, yada, 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 they concluded this, right? So that's their reference point in time for the 660, right? And that's why they're referencing the 1988. Usually you're not going to have to work that hard to figure out what's going on. Does that make sense? Yeah. Yeah.
Well, the second to last sentence doesn't give a reference of the time.
Right. So he's saying that if they were asking about 1988 and 660 was in reference to today, you'd have to subtract off the difference in time, which is why he came up with 628. Right. But the sentence before it says the 660 is in reference to 1988. So I know the paragraphs can be annoying, but just make sure that you're reading for detail in there. Okay. We do okay with those, with that one. Okay. Then let's go ahead and jump down to number 4. This one's a little bit different. Still modeling population, still using, rates and differentials and those kinds of things. But in this case, it asks for something different, okay? So in this case, we're gonna work with both a birth rate and a death rate. And you can see how these population models can increase in complexity pretty quickly, right? So if we just essentially, when you're talking about the population where it says it's growing proportional to however many are there, right? Whatever the number of population is, that is something that is growing without bound, right? We get something that's exponential. And that typically is the representation of a population that has no environmental concerns, right? So it can grow exponentially. Usually things like bacteria, mold, those kinds of things that have unlimited resources to expand compared to, what their population is. Anytime you have a closed scenario in which now there's only so much food, or there's only so much air, or there's only so much of certain resources, right? So much ground that you can grow through. That's going to do things like limit our population. So that's going to increase the complexity of our models. So you're going to see that these are going to start to develop and change. And one of the first things that you can do is talk about a population in relation to its birth rate and its death rate, okay? Because a population has people being born and people dying, or organisms being born and organisms dying. And so that's what you're getting here. You're adding a birth rate and subtracting a death rate, and that's going to create the net change in your population. Now, for this particular problem, we're going to go ahead and say that each of these is proportional to the population. So we're going to go ahead and just substitute in K1P and K2P, just assuming that the population, the birth rate and the death rate are still proportional to the population. It's just they have different proportionality constants, right? So we have a K1 and a K2. So all we're going to do here is we're going to sub those in and go ahead and solve that. So I'll let you guys get started for me, and then I will show you what I've got going. All right, so all you're doing for part A is you're plugging in what I've listed there for ddt and what I've listed for ddt. Your strategy here should look similar, right? You've got your K1P and your K2P. Go ahead and factor out that P. So you have K1 minus K2 is now just like a new constant, right? And that way I can divide by P on both sides and multiply my dt to separate. What that does is gives us the natural log of P on the left and K1 minus K2 times T plus your constant on the right. So now you're going to treat K1 minus K2 as kind of a new constant. All right, so then you're taking your E of both sides. That's going to give me P on the left. E to all of that on the right, that constant's going to come down. And then you have E to the K1 minus K2 T. Now we're not told much of anything about the population. And so we just know that at time 0, we're going to just call it P0. And we know that that's going to end up here, right? When you plug in 0. So that means that P is going to be P naught E to the K1 minus K2T. And then we want to answer whatever questions up here. So that's our letter A, solve for P of T. And then we want to analyze the cases, what happens. So when you get K1, now that's a K1. We know that K1 and K2 are both positive values, right? So we want to say what happens if K1 is less than K2? What do you know about that exponent for the exponential? It's going to be negative, right? So what do you know about your population? It is going to decrease over time. So decreasing population. If K1 and K2 are equal. Yeah, the population, so K1 minus K2 becomes 0, e to the 0 is 1. So your population results in a stable population or a constant population. P equals P0, right? Whatever that initial amount was. It's not going to change. And then if you have K1 being larger than your K2, you have an increasing population, right? Because your birth rate is now higher. You're birthing more babies than you have old people dying or people dying in general. And so you have an increasing population. All right, so still linear, just adds a little extra layer to your population dynamics. If we want to do more than that, then we're going to end up in situations that are non-linear. Anyway, let's move on there here. All right, so this one is your logistic equation. So many, many, many things are modeled using the logistic equation. often because it can be representative of population times, probability times, where the rate of change, if P is the probability, and the rate of change is the probability of something happening, and 1 minus the probability is then the probability of it not happening. So that lots of things are modeled this way, okay? But this is something that becomes nonlinear, right? So first order, but if you distribute this P, you get A times P minus B P squared, right? Which makes it nonlinear because of the P squared, right? So a couple of things that we can do here though. The nice thing is that it is separable. It's also Bernoulli's. So we do have multiple options here in terms of solving. But one of the things I want to do first is we've seen this one actually as way back in chapter 1, because you can actually look at what's going to happen with solutions without solving it, right? So if we take a quick peek at the direction field, right, this is an autonomous DE. So you can set the derivative equal to 0, and you'll have P times A minus B times P. And then set those two equal to 0. So that's going to give me P equals 0 as an equilibrium solution. And it's going to give me A over B. For now, let's assume that A and B are positive, so that we can sketch it. If we assume that A and B are positive, then our direction field is going to have two equilibrium solutions. We have one at 0. And that should make sense for any population model, right? If your population hits 0, it shouldn't magically come back, unless you have something going on like you're restocking the fish in the pond, right? So if you're allowing the population to grow normally based on things that are happening within a closed system, then if you hit 0, it should stay 0. So 0 should be an equilibrium solution. And then we should get some solution up here that actually represents your carrying capacity. Right, so this typically is going to be our A over B in this case, and this typically represents your carrying capacity of whatever the environment is there. And then we can check to see what's happening. So if you check for something that is less than A over B, so if P is less than A over B, right, then PB is less than A. So I'm looking for what happens between, right, between the 0. I'm going to assume that P is positive, but it's less than A over B. So I want to know what's happening in between. If PB is less than A, what happens to what's in parentheses? It's positive, right? A is bigger, so you get a positive. We're assuming that the population is positive, so your derivative is going to be positive. So we get something that looks like this. They end up with a little bit of curvature to them. So you're going to approach that carrying capacity. So as long as your population starts below your carrying capacity, it will increase and find that carrying capacity, and then it won't go past that. If you start with something that is less than 0, if P is less than 0, then the P out front is going to be negative. A negative B times a negative P gives you a positive value. Add to A is positive, and a negative times positive is negative. And so that means down here, you're going to move away from 0. Which doesn't really matter because we don't really talk about negative populations. So it doesn't make sense for our scenario. But if we're completing the direction field, that's what it would look like. And then the last case you want to consider is what happens if P is greater than A over B. That would mean that PB is greater than A, but a positive population. So a positive times PB minus greater than A means it's going to be negative in the parentheses. So you're going to get something that's negative. And so it's going to approach, it's going to come down to this equilibrium solution. And what that means is that as long as you start with some sort of positive population, if it's being modeled this way, it's going to approach that carrying capacity of whatever A over B is. So that's what should happen if we look at the long-term behavior of our solution we should end up with something that where the limit is a over b, right? Okay, so let's go ahead and solve the separable equation. So I'm gonna go over here, and you've got dp dt, and I'm gonna leave it factored, a minus b times b. I'm gonna go ahead and solve this. There are no t's at all on the right-hand side. A and b are parameters. P is your dependent variable. So we can divide by everything on the right and multiply by dt. So that's going to give you dp over p times a minus bp is equal to dt. Now we're ready to go ahead and integrate that. The dt is straightforward, so you're going to get a t plus c on the right. On the left, which integrating technique am I going to use there? Not u sub, not by parts. Because it's in the denominator, it's got to be partial fractions. Okay, so you're going to decompose this as a over p plus b over little a minus bp dp. You're going to find your values. So that gives you b times p plus capital A times little a minus little bp equals 1. So when p equals 0, you get little a times capital A equals 1. So capital A is 1 over little a. When you let p equal a over b, then the coefficients of the a, capital A will go away. And this will be b times a over b equals 1. So multiply by the reciprocal. That tells you that capital B is little b over little a. And then you're plugging those back in for your capital A, capital B, and integrating. They both have an a in the denominator of that fraction, so I'm going to move that out front. And then it's just 1 over p plus little b over a minus bp dp equals t plus a constant. And then I'm going to, oops, didn't mean to do that. All right, from here, I can actually multiply the a to the other side and make this a t plus a constant. So I don't have to worry about that fraction. And then this becomes the natural log of p. And I don't need really the absolute values because we're talking about population here. And then this one here is a baby u sub. If you take a u sub for a minus bp, then your du is negative b dp. And that means that this is minus the natural log of a minus bp equals, oops, sorry, I have an equals in there. And then you can put those two back together. You have subtraction of your natural logs. So that becomes the natural log of p over a minus bp. equals AT plus C, and you can take the exponential of both sides. So P is equal, P over A minus BP equals some C times E to the AT. From there, we can multiply the denominator over, and you can kind of solve for P if you want. But I'm going to leave it there for now. But you could multiply by the denominators and then combine, put your P terms together, factor out, and divide, and you get something in terms of exponentials. And then if you take the limit, you can actually see that it does in fact go to A over B. So this one separates easily, but then the integral is partial fractions. And I know without numbers, it makes it a little trickier to work with, right? But we can take our time and work our way through. All right, number 2 is the same exact thing, only now you have numbers in there for A and B, right? So the number of supermarkets throughout the country are using a computerized checkout system is described by this IVP. Use the direction field to predict how many supermarkets are expected to adopt the system over a long period of time and sketch the solution curve. So I'll let you go ahead and do that since we just did that example up top. So go ahead and sketch your direction field to find out how many over time we expect there to be. All right, on this one, when you set it equal to 0, you get n equals 0, which you expect, and whoops, n equals whatever 1 over 0.0005 is, that's 5. Tens, hundred thousands, 10,000s. So it should be 2,000, right? And so that is your equilibrium solution up here, right? So you get 0 and you get 2,000, and we know that it'll do something like this. Right? And so long term, we expect there to be about 2,000 grocery supermarkets using this system over a period of time. And then when we come in on Friday, we'll go over homework, we'll take the quiz, and then we'll pick up here, we'll solve some more things. Okay. So nothing new, just homework from substitutions and quiz. And I will grade all the homework and all the things.